we have that straightened away now. Okay, Sarah did show up, obviously. But Megan's still not here. All right, I told you last night that we would pick up with Copernicus. Oh yeah, Tioni, we do have to sit down and spend some time talking about, like the policies that are in the syllabus and that kind of stuff. Yeah, don't want to just give you that and say, yeah, go figure it out. Okay, so picking up with Nicholas Copernicus, depending on what language you're talking, I believe. You can see here it said Nikolai right there, but then on the stamp over here it says Nicholas. So different languages for his name. What was special about Copernicus?
He figured out that Earth was not the center of the universe.
Okay, he's the modern person that revitalized the idea that the Earth is not the center of the universe. What did he believe was the center of the universe? The sun. Nowadays we say, well, the sun is the center of the solar system and not the universe. So we don't still go with him exactly. And it wasn't his idea. Remember, Aristarchus, well before the time of Christ, had posited that the sun was the center of our orbit. But people said no. Why did they say no to Aristarchus?
Because that was heresy.
Well, no, it wasn't heresy.
Because they couldn't see the sun.
Okay, they didn't see the parallax motion of the stars. They didn't feel any motion. They said, we don't feel it. We have a good observation. We can't see it. Why didn't they see the parallax motion?
They were too far away.
Yeah, too far away, and they didn't have the refined instruments. We will see when I get to Tycho Brahe here in a minute, the world's best observatory from something like the 1600s. Yeah.
So when if this question were to come up on a test, okay, what I'm asking is, did he popularize it or did he come up with it?
He didn't come up with it.
Right, so should we remember that he popularized it?
Yeah, and I won't try to trick you,
Okay.
right? I won't try to get you to say Copernicus came up with the idea.
Right.
I'll if I say popularize, you'll know. Oh yeah, that's Copernicus, as opposed to.
So this won't be a metric test.
I've never taken a class from the gentleman, so I don't know what you mean.
Very good answer.
All right, so Copernicus, 1473 to 1543 is the time he lived, and we have that heliocentric model. The Copernican model was also not initially accepted. Why wasn't it accepted? Now you can say, Eliezer.
Because it was heresy.
Because it was heresy. It was heresy because the Catholic Church had built a theology adaptation to the model scientists had that said hell was below and heaven was above. And so everything had to be going around us. It all revolved around the earth. But the heliocentric universe gave a nice, easy explanation for this retrograde motion. Normally, remember I said the planets move across the sky, viewed one night to the next night to the next night. They make a constant march going eastward. But for short periods of time, they will go westward, and that's the retrograde portion of the motion. And like I said, if we had already had this is what we would have done for lab last night. When you have two planets orbiting about the sun at different speeds, the relative velocities of those planets cause the angle you view it at to make it appear to go backward, even though it is still going forward. And so the explanation for retrograde motion is very simple enough that we can do it in lab, using the Copernican model. And so sometime when we have bad weather again, we'll do that so you can exactly see how it works. So right now, I obviously want you to understand what retrograde motion is and that it is explained by the relative motions, but it'll make more sense when you actually can do it in lab, I believe. Otherwise, I wouldn't have you do it in lab. That was quite a delay between. Anyway, our first clicker question. And you can answer now. I'm sorry, it wasn't open when I first started there. The Copernican system was no more accurate than the Ptolemaic system in predicting the positions of planets because blank, just as in the Ptolemaic system. This would be something I talked about last night. 33. Do you have your clicker, Caleb? Yeah, there we go. And do you not have yours with you, Tim? Okay. Because I have one registered for you. Okay. We had then 2, 2, 8, 0. And the majority here was correct. Copernicus said that the Earth is moving around the sun, and all of the other planets are moving around the sun, but that they're doing perfect circles. The reason his calculations for the distances from the planets to the sun weren't exactly on, remember they were all really close, except for the last one that was on our table. Because that's what he could see. He couldn't see anything beyond Saturn. Those were all very close except for Saturn. But the reason they weren't all spot on is because the orbits aren't truly circular. And Copernicus had posited that the planets did circular orbits. And so that was his failing, the reason his predictions were no better. And since his predictions were no better than the Ptolemaic model, and people had a vested interest, they had been believing in this, and the church had built a system on it, people weren't willing to adopt his model until they had something more. So Copernicus dies, and the next person in our story is Tycho Brahe, who is a very interesting person in my opinion. You can't really tell from the pictures that I have.
He was cross-eyed?
No, but you see this funny line on his nose?
Yeah.
That goes back to when he was in college. He was in college and studying away, and he and one of his classmates got into a tiff. And back in the day, you settled your disputes in a duel. So he and his classmates get out there with the pistols, they paced off and turned and fired. And he clearly lost because he took it right in the nose. And so he lost a chunk of his nose in this duel. Now, he was a vain man. If it was me, I would do things to try to make it so you couldn't tell that I lost a piece of my nose. Right? Because I want to fit in. But not him. He took the old adage of, accessorize, accessorize, accessorize. So he had things like gold and silver prosthetic pieces made to fill in the missing pieces of his nose. So you'd see him with his bling there in the nose, not just a little ring, big chunk of his nose. Now, I always have to ask this because I think it's so hilarious. He's a college student, gets into an argument that they have to settle by shooting each other with guns. What do you suppose this argument was about?
Probably about physics.
The obvious answer would be a girl, but it's not. It's not about physics either, actually. But you're getting much warmer.
Probably like the answer to some math question.
It was, who's a better mathematician? I'm better than you. No, I'm better than you. Instead of solving a problem, they go and try to shoot each other. It's an interesting world they lived in. Not that ours is boring. So, Tycho Brahe became very, very famous not because of that, because he saw something that wasn't supposed to happen. He saw a new star called Tycho's nova. Nova being Latin for new. There it is. It's the third one. We now call it a supernova because we have a better understanding, and novas are one thing and supernovae are another. Actually, I should say novae because novae is the plural of nova. But what he saw, we now classify as a supernova. What he saw was looking up in the sky, there was a star that had not been there in the past. And it was there for a few months and then disappeared. Now, with the model from Aristotle forward, the idea was that it was perfect out there in the heavens. And you can't improve on perfection. So if you can't improve on perfection, it shouldn't change. Because any change, if it doesn't make it better, it's going to make it worse. And thus it wouldn't be perfect anymore. So their logic said that everything out there has to stay exactly the same. It cannot change. And so when you see a new star, that's violating these rules about perfection as they interpret things. Now, it does need to be pointed out. He's not the first one to notice one of these. He was just the right place, the right time for people in society to go, wow. There is, for instance, a very famous Chinese observation of a supernova that occurred in 1054 AD. Roughly 500 years before his. And astronomers in the modern era decided to look with telescopes at the place that the Chinese had noticed this. They called it a guest star because it appeared and then disappeared, after a few months' stay. And when they looked there with telescopes, they found what we now know as the Crab Nebula. And by looking at the size of the Crab Nebula and the rate of expansion that we can observe, they extrapolated backward and discovered that this Crab Nebula should have started just about the time that the Chinese astronomers had observed the guest star there. And so that gave scientists a big boost, knowing that there was this bright star for just a couple months, and now we have this big nebula, which is Latin for cloud, where the star was. So he wasn't the first one to observe. People who have studied Chinese documentation have found many, many cases where they had observed other such events, supernovae or novae. So he wasn't the first one to notice one, but he noticed it at the right place, the right time to get the oohs and ahs, because they had a worldview that said you couldn't have a change. The last supernova, at least that I know about, that's been visible to the naked eye, it was in 1987. So it's not like you get them all the time. I mean, they are happening all the time somewhere in the universe, but for us to be able to see them, you don't get them all the time. So he got fame and, he was already a wealthy family, but fame and fortune from this observation, and he parlayed this fame and fortune into the good favor of the King of Denmark. I'm working on trying to learn Danish, so maybe next summer we can go visit my relatives and I can actually say something besides "Hi." I'll say things like, "The duck drinks water," because that's what Duolingo has taught me so far. Anyway, I swear, I think my ancient ancestors must have been serfs on his land because they carry the family name of the island that he was put in charge of, Wien. And he built the world's foremost observatory because King of Denmark loved him. So what does the world's foremost observatory look like? You'll find lots of versions like this that all look different. And I think they all look different because the original must be in black and white. Because some of them he's wearing green, some of them he's wearing blue, some of them he's wearing red. Some of them, like this one, these are blue. Some of them they're white. Some of them they're brown. There's also some things that people modified that clearly were changes. But this is the world's foremost observatory. It does not look like our observatories. Now, the first thing in here is there are 3 people in the picture, plus pictures of people on the wall. So can you find the 3 people in the picture?
I think there's 4.
No.
I mean, is the king one of the 3?
Actually, that's supposed to be Tycho, but
Oh.
this here, is this what you're talking about? Is this the one you're talking about?
Yeah.
Yeah, that's part of the background. It's not supposed to be one of the people. I mean, it's all a painting, but that's supposed to be background of the painting, not one of the people actually in it.
Oh, I see. Mm-hmm.
The ones that are in it are this guy here, who's the scribe, the person who records data for him. this guy here who's helping to read instruments, you said a little kid. Could have been a dwarf. He is rumored to have had a dwarf who lived under the table there and entertained him. Very, very politically correct and forward thinking.
Wow.
And then, right here is the great man Tycho himself. Well, yes, that would be him. So, what is he doing there? He's making observations. There are only a few things here that are really important for his observations. Number one is, this here is actually a chair that you can move. So he can stay seated and move the chair to different angles for viewing. And he has a little sight here that he's sighting through. So he's looking through that window. See the window on the wall? Ta-da! You have an observatory. You have a hole in the wall, and you have something to measure the angle above the horizon. And then you sit there in your house or in your observatory, and you watch to see what passes. And you record the angle you look through to see it, and the time when it passes. And that's how they made observations. That was the state of the art, best you had going. Now today we look at that and we think, how could they even get anything useful from that? Right? They were creative people. And so Tycho would spend night after night here making observations. And he developed some of the best, most accurate observations that they had at that time. And he was taking these observations and trying to take the information and find a way to improve on Ptolemy's model. Then disaster strikes. The apparently untrue story is much better than probable reality. The untrue story is he went to eat with the king, and he really drank too much wine and had to go, but it would be rude to get up, so he stayed there and just bore down and ruptured something and, died 8 days later because of it. The truth is that's not possible. You cannot rupture, anything in your body by choosing to not urinate.
And then die from it.
Well, if you did, burst your bladder because you refused to urinate, yeah, the sepsis would get you.
But not while you're at the table.
Well, no, it's 8 days later.
Oh, he died later.
Yeah. So more likely he might have been poisoned or something like that, because as you might have guessed, he probably didn't have everybody as a fan. He was a little unique. Well, before he died, while he was on his deathbed, he designated that he wanted Johannes Kepler to be his replacement, the person who would take over his work and continue his work. So we got to know a little bit about Johannes Kepler. Kepler went to university. After he graduated, he got a job as a teacher. And he has to be hands down the best teacher ever. Because his second year, not a single student would sign up for any of his classes. And, of course, I was being sarcastic in best teacher. Just in case anybody thinks that's, a goal that we...
I thought you meant something along the lines of
why won't students go to his classes?
Assumedly, he must have been really ineffective in teaching them, or maybe mean, or unclear, something that they really didn't like.
Or too tough.
Could be. I don't think anybody knows why they didn't take them. I'm just saying, or take his class. I'm just saying, since nobody took it, it had to have been some kind of problem. Now, he had a lot of interesting things about him as well. Things like, he made money by doing horoscopes, which a scientist would say, well, that's not scientific. But his point was, hey, I understand where the stars are going to be. I can make stuff up. That's all you need to have for astrology, right? This drawing here is something that drew Tycho Brahe to him. Now, it's scientifically useless. But what he did was illustrate that by using your standard shapes, you have the regular solids, that you could make a system of these shapes with each of the spheres, as talked about by Aristotle, inside one and out, one's inside and one's outside for each shape. And so the cleverness of that is what drew Tycho to him. So Tycho Brahe hired him to come work with him. And he worked with Tycho Brahe for about a year before Tycho died and left his stuff to Johannes Kepler. Now, of course, if he dies and bequeaths everything to you, it should be yours, right? But Tycho's family fought that. And there was a long court battle about who got what. And in the end, Johannes Kepler just kept the data and didn't give it to them. I think the family got everything else, but he just kept the data. And he was actually trying to continue Tycho's work to honor Tycho Brahe. It wasn't like he was vindictive. But what Kepler discovered was some very interesting changes that that convinced scientists the sun was the center. So things that he discovered were, number one, the planets move about the sun on elliptical paths. Not circles, but ellipses. And they have non-uniform velocities. That is, actually I should have put non-uniform speed, because if you're going a circle, by definition you're changing direction, that means changing velocity. But non-uniform speeds, that is, the planets speed up in some parts of their orbits and they slow down in some parts of their orbits. The model of Copernicus had circular orbits with constant speed. So those are some pretty big differences. He actually has 3 laws of motion. And these 3 laws came simply by looking at the observations that Tycho Brahe had made. And if you think about it, he had to have been super intelligent because he saw patterns that no one else saw. And that's really the measurement of intelligence, is seeing patterns in obscure situations. We can all see a pattern when I get up on Sunday, I'm tired. Get up on Monday, I'm tired. Get up on Tuesday, I'm tired. You start to see the pattern, right? I'm tired when I get up. That's not genius. But seeing these kind of patterns, yeah, pretty genius. So first we have to describe what an ellipse is for the not circle but ellipse to make sense. Some of you may know, but an ellipse is essentially an oval. It's a mathematically defined oval. The mathematical definition is very simple. If you have 2 focal points, so we call them foci, in an ellipse. And you could always make an ellipse. If you're stranded on a desert island, and for some reason you decide, I need an ellipse on this island, you can make one. All you have to do is put 2 posts in the ground, then spend the next week, taking leaves and whatnot to make yourself some rope, and tie one end of the rope to one of your posts and one end to the other, and then you just walk out keeping the rope tight as you go around, and the shape you'll walk out will be an ellipse. Right? The distance from one focal point to any point on the ellipse to the other focal point, those 2 always add up to the same amount for an ellipse. So that's why it'd be really easy to make your own ellipse. Got it? So when and if you get stranded on that desert island, you now know how to make an ellipse. Now, ellipses have a long axis, and the long axis is called the major axis. They also have a short axis, going like, yeah, and that's the minor axis. In astronomy, we usually don't talk about the major axis and the minor axis. We talk about the, there we go, semi-minor axis and the semi-major axis. So here you have the major axis, the minor axis, and you can see the semis for those. So the major axis is longer, minor axis is shorter. The major axis is the longest line you can draw between 2 points in an ellipse. The minor axis is the shortest line that goes through the center. You have to specify through the center, or you could do something like this. So that's what an ellipse is. Now that I've explained it all, how many people knew what an ellipse was and that was just wasting your time? Oh, excellent.
It was fun.
Okay, so it wasn't... Okay, you guys don't know the Eagles anyway. a really nice song.
Wait, who listen to the Eagles?
The Eagles have a song, Wasted Time. The eccentricity of an ellipse describes how eccentric it is. Let us suppose that I were to say that, we'll choose Dr. Rose. That Dr. Rose is an eccentric fellow. What would that mean?
It's weird.
Okay, he's a little out there, a little weird, a little odd. The eccentricity is measuring how odd your ellipse is. And by odd, we mean different from circular. So if you have an ellipse with an eccentricity of 0, it would be a perfect circle. And an eccentricity of 1 would be super elongated. It would be essentially a flat line going back and forth. And so the eccentricity is actually calculated as the distance from the center to a focal point divided by the semi-major axis. You see the equation right there for eccentricity. So it has a mathematical description. It is important that you know what eccentricity means. When we talk about things like the orbits of the planets, we'll talk about their eccentricities. An eccentricity of 0 means it's a perfectly circular orbit. An eccentricity of like 0.2, that's the eccentricity of Mercury, is a little elongated. An eccentricity of like 0.7 is quite elongated. We don't have any orbits like that in our solar system, except for with comets. When we talk about galaxies, they will classify elliptical galaxies by their eccentricities. So you'll have things like an E7 galaxy. The E7 means it's elliptical with an eccentricity of 0.7. So there's some importance to understanding that. And, I should move forward now and get this website going. Crap. Have to quit my presentation to go to the website. I want to show this website here so we can have fun with it. That shows us properties of ellipses. Okay. Back to the presentation. Okay. His first law, Kepler's first law, was that the planets orbit the sun with the sun as one of the focal points of the ellipse and doing eccentric orbits. His second law says that a line that goes from the sun to a planet will sweep out the same amount of area per unit time. So that means like if you have the planet is here and 1 month later it's here, then if you take the area swept out by the line that connects the sun to the planet, so this area that's in blue, that would be equal to the area if it was out here and you used 1 month separations. If it's farther away to get the same area, you have to have a much smaller distance it travels in the time. So the rubber meets the road outcome of this, the thing that's important for you to know about this. You should know that the area swept out per time is constant. But the important thing is that second law says that a given planet travels faster when it's closer to the sun and slower when it's farther away. Or if we consider a comet, when a comet is close to the sun and has its nice pretty tail, it's going a lot faster than it's far away from the sun. So you have something like Halley's Comet that comes by once every 77 years or so. And its time that it spends close enough to the sun for us to see a pretty comet is measured a couple months. The time it spends out there is over it's over 76 years. So you know it's going super slow out there compared to how fast it's going when it's near the sun. And that's because of Kepler's second law. Kepler's third law, you have a question?
Yeah, so in essence, Mercury and Venus are going faster than the Earth.
Well, this is for a given planet.
Oh, okay.
For a given planet in its orbit.
Okay.
It doesn't compare one planet to another planet with the different orbits.
Okay.
And so the comparison there actually comes along with the third law. The third law says that the time to orbit, the period, squared, is proportional to the distance from the sun, cubed. Now you can take that, I'm not going to right now. Once again, when we do that lab, you'll do the calculations and see how the speeds compare. But this one here says that if you know how far a planet is from the sun, you can calculate how long it takes to orbit around the sun. Or if you know how long it takes to orbit, you can calculate how far away it is. And so this A is actually, in truth, the semi-major axis. We tend to talk about the semi-major axis as the average radius, but it's not really the radius. If it was a perfect circle, it would be the radius. So that's Kepler's third law. It's a nice mathematical relationship. Notice some important things about units. This equation here has the period, the time for one orbit, in units of years is equal to the distance from the sun, well, period squared, distance from the sun cubed in units of astronomical units. Now, for units' sake, how long does it take for the Earth to orbit the sun once?
1 year.
1 year. So in years, the period for the Earth is 1. How far is the Earth from the sun in astronomical units? 1. So for the Earth, this would be 1 squared equals 1 cubed, or 1 equals 1. Right, so that works out. The reason we do it in years and astronomical units is because we're just using the Earth as our comparison. And so we took the two values where it's 1 for the Earth. And then if you take something like Mars, I believe Mars is about 1.5 astronomical units away from the Earth. So if it's about 1.5 astronomical units away, we can calculate its period. I can simply take, for Mars, so the period squared is equal to a cubed. If I want to find the period, how do I get period if I had period squared? Take the square root. So I take the square root on both sides. Now you probably know that for the square root, right? There's actually another way of writing that. I can divide by 2 for the exponent. So either one of these give me the same relationship, that the period is equal to the semi-major axis to the 3/2 power. And so then I just take my calculator, and I know you guys can't see my calculator, and I take 1.5 and raise it to the 3/2 power, and I get period is equal to 1.84 years. So the time for Mars to orbit around the sun is 84% longer than the time for Earth to orbit around the sun, even though it's only 50% farther away, based on Kepler's third law. So that's one that we're going to be doing some calculation with from time to time. The first two laws we won't be doing calculation with, we just need to understand them. But the third one we need to be able to do calculations. Now, for Ken's question, since I'm halfway here, I will finish out. If I want to calculate the speed for Earth in wacky units would be the circumference of the Earth's orbit, 2 pi times a for the Earth, divided by the period for the Earth. So that would be 2 pi times 1 astronomical unit divided by 1 year. Now, nobody uses speed in units of astronomical units per year, right? That's a wacky unit. But for comparison, it allows us to compare. So now if we do the same thing for the speed of Mars, we have 2 pi semi-major axis for Mars divided by the period for Mars, and that's going to be 2 pi times 1.5 astronomical units divided by 1.84 years. 1.5 divided by 1.84 is less than 1.
How do we know that 1.84?
I just calculated it right here. I calculated that from Kepler's third law. Remember I said Kepler's third law is what actually gives you the answer to your question? And so because Mars is farther away, it's actually going slower than the Earth. So the closer planets are traveling faster, but it's because of this relationship, not the other one. That's, of course, assuming I made no mistakes, but I don't think I did. Okay. Things that Kepler's second... actually, this is a clicker question. All right, things that implies... Wait a minute, that doesn't imply all of these. So give me a second to get there. Okay, you can answer now. Okay. We got 8, 0, 4, 0, 0. And the majority's right. It's always a little reassuring when the majority's right. Kepler's second law was the one that said the area swept out per unit time is constant, which has the rubber meets the road importance to you, that planets move faster when they're on the part of the orbit closer to the sun, slower when they're on the part of the orbit farther away from the sun. Okay, now let's go to that website, which I'm going to have to change this to. And pray that all stays well. All right. This here is part of University of Nebraska Lincoln's astronomy stuff. And this is a simulator to show how these laws work. So the first law says that the planets orbit the sun in elliptical orbits with the sun at one of the focal points. Now I can show here, there's the other focal point in this picture. Throw the semi-major and semi-minor axes on if you want to see them. And I'm also going to put the center there. You can see the center of it. It looks a lot like a circle, doesn't it? But it's not. If I show these radial lines as I run the animation, you see that it's clearly not circular there. It's going much slower. Well, it's going faster now, and then it slows down. It's going much slower out here when it's farther away. Why is it going slower when it's farther away?
Farther away from the sun.
And in terms of Kepler's laws, that would be Kepler's second law, right? Now, some things we can do with this. I can make it so it simulates Mercury's orbit. Now, Mercury is close to the sun, and so it has a shorter period. Hence, this thing is whipping around pretty quick. Notice it has an eccentricity of 0.206. Now let's mess with this. I said a small eccentricity has what shape? Like a zero eccentricity has what shape?
A circle.
Circle. So if I bring it to 0, there's a perfect circle. Notice those two lines just aren't separating because they're both coming from the same point. It's doing a circle. If I go out to a large eccentricity like 0.7, you see that it's very much not a circle. Anyway, you look at that and say, yeah, it's not a circle. So you can tell the 0.7, the 0.2, it doesn't look that off. Venus has a bigger orbit, so it's going slower. You look at these, you still don't really see a separation because its eccentricity is 0.007. That's really close to 0. very close to circular orbit. Go to Earth, our eccentricity is 0.017. Pretty close to circular, but see, you can see those two separating. They're not perfectly on top of each other. Check out Mars, eccentricity 0.093. It's less circular than Venus or Earth in its orbit. Go out to Jupiter, and Jupiter is really far out there, so it's slow. I'm going to speed up my rate so that we don't have to stay here all night. Question, Ken?
So what time of the year is it going the fastest?
Well, it's going to go fastest when you're closest. The perihelion is when you're closest to the sun. And for the Earth, that's, remember I said my ex-girlfriend's birthday? Somewhere around January 4-ish is when we're closest to the sun, hence going the fastest. Go on to Pluto. Pluto is way out there, but it's also very eccentric, 0.249. And if you look at the orbit of Pluto, it actually still looks, to my eye, fairly circular. But when you look at where the two foci are, you see that they're pretty far apart. And you see it's going super slow because it's very far away from the sun. Now let's go to Kepler's second law. And we won't do it with Pluto, we'll do it with Mercury. But I have to slow it down. Yeah. What we don't want is to have somebody, have seizures. So, remember, Kepler's second law says that the area swept out per unit time is constant. So I'm going to start sweeping now and now. And if you look at this, what you should note is this distance here is a smaller distance than this distance here. They're the same amount of time, so if this is a bigger distance, it had to be going faster at that point. And the area, and of course you have to take it on faith that this is accurate, the area that's in whatever color we want to call that, magenta, is the same as the area in whatever color we call this, emesis. Everybody knows what emesis means. You know what it means?
No, I'm impressed that you know more than that.
Yes, well, on the ambulance we had emesis bags for people who toss their cookies. I don't think that's an official color. So here we're seeing a simulation of Kepler's second law. Now Kepler's third law, this here is just a graph showing the relationship between period and semi-major axis. You can, change the semi-major axis to see it move on that, but that's not super exciting. The Newtonian features, I'm actually not going to have time to talk about that today, so I won't. That's the last time you guys, You've already answered that one. So moving forward, Galileo Galilei. And yes, I just love to say his name, Galileo Galilei. Galileo is famous for his work with the telescope. It's important to me that you know he did not invent the telescope. It was invented by people from the Netherlands. But he heard about it. He made his own and improved telescopes. He's the first person to use them for systematic observation of the sky. Another really important thing about Galileo is he's the person who really set up the scientific method for determining scientific information. We talked about models of Aristotle and Ptolemy and whatnot, but it was Galileo who said, my model is not worth anything unless I test it, and the tests show that it's reliable. And so our scientific method, and let's review on what the steps were we've talked about. What was the first step in my simplified scientific method? Observe something interesting. After you observe something interesting, what's our second step?
Say something smart.
Not say something smart.
Make like an educated prediction.
Make a hypothesis or educated guess that's based on scientific ideas that explains why the observed thing happened and makes predictions that you can test. And then what's the next step? Make a test that will test a different prediction. You don't make a test that tests your observation. You already made the observation. You make a test that tests a prediction of your hypothesis. And what happens if your hypothesis passed the test?
Make another test.
You make another test. What happens if your hypothesis fails the test?
Make another hypothesis.
Make another hypothesis. You have now more information because you know, well, it's not that. It's something else. And so if it fails, you're narrowing down your options. If it passes, you're building your confidence. So when is this process done?
Never.
Never, ever. You never can prove something right with science. You can only prove them wrong. We can give Galileo credit for developing this systematic way of studying the universe. Now, those laws of Kepler gave spot-on predictions of where the planets would be. Copernicus didn't give spot-on predictions. They were just as bad as the Ptolemaic model. Kepler's gave spot-on predictions. So scientists started accepting that the sun was the center. And Galileo is right now important in our discussion because he was a person who publicized that view. How did he do it? Well, we start off with Galileo had a good friend who was a cardinal. And they would talk science all the time. And then, lo and behold, that cardinal becomes the Pope. And so Galileo wants to write a book about his heliocentric belief that the sun is the center of the universe. And you couldn't really publish a book without having the papal imprinter. The Pope said, yes, you publish this book. And so he talked to his friend, and the Pope said, okay, you can publish your book, but you can't just give your side of the story. You have to also give my side of the story. By the way, when I teach origins, I make sure that I talk about my side of the story, the Christian story, and the science side of the story, and leave it to the people to decide what they believe. So the Pope said that's what you need to do. So Galileo writes his book, which is often just called, Dialogue. It's got a pretty long title, but in this book, he has three main characters. One of them is very wise, and he gives you Galileo's viewpoints. One of them is very simple-minded. His name is Simplicius, or something like that, meaning simple-minded. And he gives the Pope's arguments. And then one is logical, and he always says, well, clearly Galileo's argument is right. And so the book is published with the Pope's approval. And, Ruth, what? He's mocking me. My friend Galileo's mocking me. And so Galileo then faced the music. He was forced to recant. That is, to say, I was wrong. My ideas about the Earth orbiting the sun were wrong. Because he had mocked the Pope. Now legend has it, as he's kneeling down saying, I'm right, he muttered under his breath, but it still moves. Because, he was that kind of guy. Now, he loved to put people down who he thought were wrong or unintelligent. That's really what got his butt in the sling. And we'll have to stop there. Remember